Step function of RC and RL circuits. What is a step function? At time 0, the voltage or current source goes from 0 volts or amps to a non-zero value instantaneously, and then stays at the new value for a long time. Instantaneous can be defined as much less than tau of the system, and a long time can be considered 5 tau. And so what I have here is I go from 0 milliseconds, 0 volts, I go up to 1 volt, and it almost looks instantaneous, but if you look carefully, you can see there is a less than infinite slope. And it goes on for 50 milliseconds. So if I think tau is 10 milliseconds and I keep this pulse on for 50 milliseconds, that's 5 tau. So if I do this step function in LT-Spice, here we have the file that you can download for an example. I have a pulse that goes from 0 to 1 volt with a 0 delay with a variable of rise time. The fall time is set to rise time as well. And this is the pulse width, and that's the period. And you can see I have R1, C1, which is obviously R1, C1 is tau. ST is stop time, which is 10 tau. Rise time is tau divided by 100. That can be considered much less than tau, just dividing by that. The pulse width is 5 tau, and the period of that pulse width is 10 tau. So this was the simulation from the previous page, and if I zoom in, you can see that there is a slope that is less than infinite. And it looks instantaneous, but it's not. But it's good enough. So when I plot the output of this circuit, V2, you can see that this was a good approximation of the rise time being 100 times less than tau, the pulse width being 5 tau, that the circuit most certainly gets almost up to where it needs to go, and it almost falls down completely back to 0 for another 5 tau. So in order to understand the next part, we just have to review the DC high frequency values of capacitors and inductors. And at DC, a capacitor acts like an open circuit, remembering that a capacitor is 2 parallel plates separated by a dielectric. Well, that sounds like an open circuit to me. At DC, an inductor acts like a short circuit. Well, what is an inductor? It's a wire wrapped around a core. Well, wires can be considered shorts. At large frequencies, a capacitor acts like a short circuit. If I take the Laplace of a capacitor, it's 1 over SC. S representing frequency. The higher S goes, the smaller this equivalent resistance gets. And at large frequencies, an inductor acts like an open circuit. So if I take the Laplace of an inductor, it's SL, and as the frequency goes up, so does this characteristic impedance. So let's try to do the step function of this first order circuit. We'll convert to the S domain, where we have 1 volt step function given by this. R1 is still 1K, C1 is 1 over SC1. And in order to find V2, I can really just use voltage division. Here's my initial voltage. This is my impedance here, divided by the sum of the impedance. And when I simplify, I get this. And the thing is this form you cannot look up on most tables. You have to break it up into its characteristic equations. So you have something like V1 over S minus V1 R1 C1. And to go from here to here is a bit of algebra, but there's an equation for it, and it's straightforward. Well, once I have that, and then I simplify, I really have V1 over S minus V1 over S plus tau, which really, if you recall, that was the original step function, and that's the minus of the natural response. And here's the full response there. So this is pretty interesting because I have the DC value of the step response here, and this is the natural response, and it's just 1 minus that. So that's a curious example. Let's see if that checks out for other first order circuits. So here we have two resistors, and we have a capacitor here, and at time equals 0, V0 V2 at 0 equals V1 at 0 equals 0 volts, and the long-term response at V2 infinity, V1 infinity equals half a volt. As you can see, if this goes up to 1 volt, that resistive divider will be half a volt, because at DC this is an open circuit. So the natural response when V2 at infinity is 1 volt, and we can see that we've charged this capacitor up. Now we're going to discharge it to find the natural response. That tau, if you notice, R1 and R2 are in parallel now, and that tau, rather than being previous examples R1C1, it's the parallel combination of these. So the natural response is 0.5 e to the minus t over tau, remembering that it 1 volt voltage divider. So our step response is 0.5 minus 0.05 e to the minus tau t divided by tau. And so, yes, for these first order circuits, if you take the long-term step response and subtract the natural response, you get the full step response. Well, we can look at this in LT Spice, and we can see that in 5 tau we go up to a half a volt, and in another 5 tau we come back down to 0, because tau is, in this example, 5 milliseconds. We can even apply this intuitive analysis to when there is an offset, where in this case I didn't start at 0 volts. I started I went from 1 down to minus 1 and 0. And you can see that this gives the characteristic equation.